the three-part sequence of one line of these works by Amit, Rachel, and Ayush, and Amit will start over.
All right, thanks. Can everyone see the screen and hear me?
And again, if some people join now, let me encourage, if you're a participant and not a panelist, you want to participate, you want to ask questions, raise your Zoom hand, and the good folks at Simons will promote you to a panelist. If you are already have the ability to show your video, if it's at all comfortable for you, I will be grateful, and I think the speakers would also be grateful for you to turn on a new camera so they don't feel that they're just talking to a bunch of icons. And yes, and feel free to just unmute yourself and ask questions during the talk.
So I just want to confirm before I start that everyone can both hear me and see my slides. Can someone please say something about that?
Yes.
Okay, great. Thank you. All right. So, with that excellent introduction from Yael, first, before I say anything actually about our work, it is just so true what she said. I think this is really all the stuff that we're going to be talking about is a victory for the community. It was really an incredible, patient community effort in which there were a lot of people who really did, fight through quite challenging environment, including a number of people who were students when they were working really, really hard on this, and therefore actually had to deal with what Shafi was talking about, which is some resistance, some significant resistance, to put it mildly. And yes, it's really a community effort. And what I'm going to be talking about today, in the first part of this talk, is just an awesome 2+ year collaboration with Ayush and Rachel Lynn, who you'll also hear from after me, about our result that gets IO from well-founded assumptions, as Yael already told you about. So let me, since Yael has already introduced everything, let me just jump straight into it. And again, please stop me, please ask me questions. This is definitely the right way to go, and it's really fun to see that in this workshop. So we will show that IO exists, assuming sub-exponential hardness of all of the following assumptions: LPN over ZP, LWE, PRGs and NC0, and the SXPH assumption. I'm going to go over all these. So the main focus of my talk is to talk about these assumptions, and then also talk about this key pseudorandom object and sort of one aspect of it. And we're going to hear more and more about that as our sequence of talks continues. So, so again, just sort of pictorially, as Yael alluded to, really the key new thing that we built in this new work is a new pseudorandom object. And I'm going to talk about that, and you're going to keep on learning more and more about that. And we're basing it on these 4 assumptions, and it'll really be the LPN and PRG and NC0 assumption that'll be critical for the building of this new pseudorandom object. LWE and SXPH were mostly used in prior works that we build upon many such prior works. So just with no further ado, let me just jump straight into the sort of key assumption, the assumption that really made this work possible. That's why Boaz, called our scheme the LPN based scheme, because the LPN is sort of playing a really key role. So what is this? What is the LPN over ZP assumption? This is the learning parity with noise assumption, LPN assumption, has a long history within cryptography, dates back to the work of Blum et al. In 1993, who looked at it in the case where P equals 2. And then in a joint work with Yuval and Manoj, we looked at it in the general case for larger prime in cryptography. However, the actual assumption goes back much further. The ideas and the assumption behind it goes much further in information theory, back to the classic work of Hamming and work from the 1950s, where the idea of linear codes and random linear codes over large fields, over general ZP, were introduced. So again, back in the 50s, all this stuff was being discussed. So just to review the most basic aspect of this, suppose we have this matrix A, and this is a tall and skinny matrix. So it has L columns, so L is a smaller number, and it has N rows, and n is some polynomial in L. And to encode a vector s, which is also over zp to the L, we just multiply. So we multiply a by s and we get the code word c. So that's why we call it a linear code. And again, if this...
Amit, are you moving your slides?
Sorry?
Are you moving your slides?
It should be on the LPN over ZP slide.
No, it's still on the, for me at least, it's on the introduction slide.
No, for me it's okay.
Okay,
Okay.
so it's my thing. Okay.
I guess this is starting to happen. Do you want
No,
me to?
no, it's my thing. My internet sort of flaked out in the middle. It's fine.
Okay.
This happened to me before, and leaving Zoom and rejoining helped do that. Yes, it's
It's my internet. It just flaked out for me. Yeah.
Okay, but if more people have that problem, then please tell me. Maybe I should leave and rejoin, so we can do whatever it takes to make this work.
Yes. Yeah, just maybe yeah, once in a while you can mention say words as we see on the slide so people understand.
Ah, very good. Yes. Okay. So as we see on the slide, we're talking about the LPN over ZP assumption, and we're talking about random linear codes. And so we have on the slide this matrix A, this vector S, and just you multiply A times S, and you get a code word C. So again, this is classic ideas from error correcting codes. Many, many, many decades of thought have gone into this. And in particular, when we think about random linear codes, where this matrix A is completely uniformly selected from ZP to the L, again, this has a very long history. And all the way back in the 1950s, in the really groundbreaking and incredibly influential work of Gilbert and Varshamov, they showed that if you have a random linear code, they actually have incredibly strong combinatorial error correcting capabilities when it is dealt with, when it's combined with sparse error. And now for the purpose of this result and this talk, let me be very concrete about what type of sparse error we're talking about. So as you can see on the slide, we have this error vector E, which is an n-dimensional vector. And this error vector is 0 almost always, but with probability 1 over L to the delta, where delta is any constant greater than 0. It's just a random field element in ZP, and otherwise it's 0. So if you think about it, what that means is that we expect something like n over L to the delta elements of E to be non-zero in random positions. But again, the vast majority of the positions will be 0. And in fact, for even much stronger, much more dense errors, it has long been known, again, since the 1950s, that random linear codes are capable of correcting such error combinatorially, but not efficiently. So again, the fact that we knew that there was a combinatorial error correcting capability, there was an information theoretic way of correcting, meant that there was an incredible amount of motivation to try to find a way to do this efficiently. And yet, in all those decades, there has been no efficient decoding algorithm that's been learned for random linear codes. And in fact, by efficient here, I don't just mean polynomial time, like polynomial in n and L, but even sub-exponential in L. There's been almost no progress. And I'm going to talk a little bit about that in just a moment. And then hopefully you'll hear even more about it later today from Benny. But because there hasn't been any progress on these decoding algorithms, there's a natural assumption, which is called the LPN over ZP assumption, which just says that if I look at AS plus E, if I look at these random, if I look at a random matrix A, and so A comma AS plus E, and this random code word that is then perturbed by this sparse error, this sparse random error, then in fact this looks uniform. So it's a pseudo-randomness assumption of A comma AS plus E looks random. Okay, and again, just to be very clear, for building IO, what precisely are we assuming? We are assuming that there exist arbitrary small constants, epsilon and delta greater than 0, such that this assumption, A comma AS plus C is indistinguishable from uniform, where the error probability is 1 over L to the delta, that holds against all time 2 to the L to the epsilon adversaries. That is the precise assumption that we're making. That's what we call the LPN over ZP assumption. And in fact, this assumption also follows from the hardness of decoding. So from the actual problem that has been worked on for all these decades unsuccessfully, there is a classic and quite natural search to decision reduction due to Applebaum et al. That shows that this assumption, this indistinguishability assumption, pseudorandom assumption, is true if it is sub-exponentially hard to recover S from A comma AS plus C. So if it's actually hard to decode S, then in fact it's hard to distinguish A comma AS plus C from uniform. And I just want to briefly mention a few more details for those of you who want to know all the details. In order to invoke this, this search to decision reduction, in order to only assume the hardness of decoding, we need to set the prime P to be 2 to the L to the epsilon prime for some tiny constant epsilon prime less than epsilon, okay? And the reason for that is that this search to decision reduction, the one that we know, of course, there could be better ones, and I think there might be better ones, but the ones that we actually know also run in time polynomial in the actual modulus P. So in order for us to invoke that search to decision reduction, we do need to make sure that the prime is small. But that's not essential to our work in any way. So if, for example, you don't feel comfortable doing that and you only feel comfortable assuming the LPN assumption against adversaries where the modulus is larger than the running time of the adversary, that's fine too. We can make that assumption and everything will still be fine in our construction. It's just, in that case, we have to make the decisional assumption, the pseudorandom assumption directly. We can't go via the search to decision reduction as of right now. Maybe there are better search to decision reductions, and that's very well motivated by our work. But as of right now, kind of those are the options that you have. But we can work for any sub-exponential setting of the prime P. Okay?
So, Amit?
Yes.
Is there any monotonicity known that, say, if P is larger or smaller, are there any reductions known in either directions, whether the problem becomes harder or become easier when...
That's a great question. And presumably we'll talk about this even more later on. But as of right now, as far as I know, there's no such relationship known. It is true that there are attack algorithms for LPN that only seem to run a little bit efficiently when P is 2, maybe a very small prime. I'm not even sure about that latter part. So it does seem, based on the algorithms that we know, the algorithms that have been constructed over the last several decades, that the larger P is, the harder the problem becomes. But there's no proof of that. There's no understanding of that. And I think this is extremely well motivated as a question for us to think about. But I am not aware of any such relationship.
Yeah, in some sense, you could actually think that larger P gives you, in some sense, more bits of information. So like roughly speaking, you could think that if log P is K, then it's as if you get a K factor of extra equations. But I don't know, usually getting K factor of extra equations wouldn't matter much. So maybe that doesn't really make a difference.
Right, yeah, I mean, that log P, because especially in our setting where log P is still like, you know, L to the epsilon prime, it's still very small. That's still a very small number of extra equations because I'm anyway giving you n equals poly-L equations, right? So that doesn't, at least again, we don't know how to make use of that information in any way, and neither has anyone been able to figure that out.
Yeah, I don't think there's any region, even if you let the bit size of P be triply exponential in the other parameters, I don't think we know anything better. On the contrary, the bigger P only hurts non-attacks.
Yeah. Yep, exactly as you've all said. And
I'll try to talk about it, but just that.
Yeah, and then
I think that the point is that all the linear algebra that we know, this is the basis for all the attacks. Kind of they don't know how to exploit this additional information, right? That's the point. Although information theoretically, you have many information. Basically, we have no other ways. At least we don't know other ways except for treating these as simple, right? As a unit bit information
Right. I also want to just mention that there is another intuitive way in which it is actually a little bit harder, which is that the EIs are more random, right? Like the EIs, when there is an error, then it's uniform over the entire large field, right? So it's not just a bit flip, but
yeah,
but
the ratio between, yeah.
Right. So in that sense, also there's some intuition as to why it should be harder, but it's just intuition. We don't have good idea. And maybe I'll mention one other little thing, which is that, you know, as I'll point out again in my slides, but as is obvious to everyone who's looking at this assumption on the slide, this looks very much like LWE, right? The only difference is that this E is sparse as opposed to being small in LWE, right? Now, but the fact that E is small in LWE does let you do these like modulus switching, right? It lets you kind of argue about LW with regard to one modulus versus LW with regard to another modulus, because you can just you know, divide and then round, and that's still a valid error. But you can't do that in the context of LPN, or at least we don't know how to do that in the context of LPN, because when you do that modulus reduction, you'll introduce errors almost everywhere, and we crucially need E to be sparse when we're reducing LPN to, you know, LPN P versus LPN P prime, right? We want to maintain the sparsity. So that's sort of the technical difficulty that that we have in terms of being able to explore how the different values of prime relate to one another.
So a question to those who study these LPN or LW generalizations: if you have a fixed entropy budget and you have to distribute it, right? So you encode, you take a random code word in a linear code, and you have to use your entropy budget. So obviously it's a big question to relate LPN to LWE, but we have more attacks against LW than we have against LPN. Do we know that LPN is in some sense best, or do we have a candidate way to distribute the entropy that is better with respect to known attacks than LPN? So if you have a fixed entropy budget, maybe doing some hybrid between LPN and LWE. No, has anything like this been considered?
These are really all just instances of a more general assumption, right? Which is just the hardness of noisy linear decoding, right? And that's a great question. You know, what is the best distribution over E with an entropy budget in terms of hardness? I don't know the answer to that question. And yeah.
I can quote Odell Regev, who claimed that the Gaussian noise should be the best one, but I don't think that
LPN should be the best. Sorry, Benny, I couldn't hear you.
No.
Benny, what did you say?
I said that, I mean, I had this discussion once with Odell Regev, who claimed that the Gaussian noise should be better than the, like, given a budget. Then
but maybe it's a budget, maybe it's ID noise or something. Maybe it's in the same, yeah.
Is better harder?
Better harder.
Yeah, better harder, yeah.
Better scripto. But I don't think that we have a formal way to show anything like it, and it's not even clear what the evidence that we have suggests.
Right. You can look at the best attacks, but we have a lot of trivial
and
attacks.
Actually that's a perfect segue for me. So in terms of best attacks, the best known attack on this assumption is again very far from what we're assuming. So the best known attack is something like 2 to the order of L to the 1 minus delta. And remember, delta is just an arbitrarily small constant, like 0.01. So the best attack is something like 2 to the L to the 0.99, right? And we're only assuming 2 to the L to the 0.01 hardness. So just in terms of where we are with regard to attacks, there's a vast gulf, despite all these decades of work. But hopefully there'll be like a renewed interest, a renewed push by all those great algebraic cryptanalysts out there. And we definitely want that. We want everything to be looked at super closely. So let's all try to attack it and get better ideas about how to attack LPN and how to relate LPN to other assumptions as well.
So who knows, maybe coding theorists will give us the breakthrough, right?
Yeah, maybe. Although again, the coding theorists are the one who've been working on it the longest. You know, they've been working on it for decades and decades and decades. In some sense, we're the stragglers. You know, we're the new people on the block as cryptographers. And in fact, just this is a slide that's just shamelessly stolen from Geoffroy, who's looked into this question much more systematically than I have. And this is just a small sample, according to him, of papers in the literature that have tried to attack LPN in various ways. And
so, I mean, just to make the point about large P, over real numbers, it's an easy problem.
excellent point. Yes, that's a great point, right? That if we want to look at this over the real, and of course, it's something we've seen in crypto over and over and over again, and especially in the context of IO, right? Sum of squares and even simpler algorithms in these settings can, in fact, efficiently decode over the reals. You can do L1 minimization. You can use like classic optimization techniques to decode efficiently if we're seeing this over the reals. So that's something that we've seen over and over and over again in cryptography, that when you introduce the mod P structure, everything changes. For example, multiplication, right? I mean, there are just lots and lots of problems that we know are hard, or exponential, like all these things, like exponentiation mod P, we've thought is hard for decades, whereas exponentiation over the reals is trivial to invert. We've known how to do that for more than 1,000 years, right, with the logarithm computation. So this is definitely one of those examples of a case where things are easy over the reals and hard over, apparently hard, over finite fields. And I'll just make one note here, which is that, in fact, over P equals 2, so for the case where you have, we're working over Z2, and for the case of significantly more dense error, so constant rate error, there was really a breakthrough work back in 2003 by Blum, Kalai, and Wasserman, really a celebrated result, where they were able to improve from an exponential attack to something like 2 to the n over log n. So it's still super far from an attack on our assumption, but it was able to sort of shave a log factor off of the exponent. And in fact, as far as I know, for our setting, for both, and really for two reasons, both because we're looking at a large prime, a large modulus, but also because we're looking at the sparser error scenario, we don't know how to even adapt the Blum-Kalai-Wasserman algorithm to even save that log factor off of the exponent. So I don't even know how to do 2 to the L to the 1 minus delta, whole thing divided by log L. Like even that's not something that we know how to do. So they're really great questions to think about here. There's been a lot of work, especially in the coding theory community, but still we know almost nothing. So so that's a little brief introduction to LPN over ZP. And again, we're going to hear more about this from Benny, I think, right, later today. And just on the slide, I'm just pointing out that, this was in pictures, and just to write it mathematically, if we have these row vectors of our random matrix A, if we call them the AIs, then we're assuming that if I give to you, the adversary, AI, comma, AI.s plus EI, then this is computationally indistinguishable from AI, comma, UI, where each UI is just chosen uniformly at random from CP. That is the assumption we're making. Okay.
So me, just out of curiosity, just for my knowledge, all this like 50 papers you put on the previous slide, yes. Basically you're saying they're like survey papers, they don't have any results, because you said basically the trivial algorithm is still the best. So right. What do they do?
So what are they doing? Yeah. So the point is that there are things you can do to shave like some small constant factor. So like a lot of these algorithms are like, oh, we can shave a factor, like instead of 2 to the, like in our language would be, instead of 2 to the L to the 1 minus delta, we can do 2 to the 0.7 times L to the 1 minus delta. So there are it's not like there hasn't been any work. There've been lots of interesting little, sorry, I shouldn't say little. There've been lots of interesting algorithmic ideas that have, tried to improve the efficiency. And again, it's such an important problem for information theorists that there really is just too much work on this. Like there's really an extensive literature here, but it's all trying to, shave small factors, shave as much as you can get. So that's what my understanding of these papers are. I have not read these papers. Again, I stole the slide from Geoffroy, but that is my understanding, having looked at very, very tiny subset of these papers. Okay. Any other questions before we move on? So actually, before I talk about the other assumptions, I actually want to tell you right away, immediately, how we are going to use this actual assumption, okay? So the thing in the blue box, that actual assumption, like this actual indistinguishability property, is only going to arise in our entire line of work in exactly one way, and it's an extremely simple way. So I want to just tell you about that right away. Sorry. Okay, I forgot to mention one more thing about LPN before I move on. So I want to remind you that we're only assuming LPN for an arbitrarily small constant delta greater than 0. Okay, so that's, for example, delta equals 0.1. Okay, and while that is quite sparse error, that is still too sparse an error to be known to imply, for example, public key encryption. The classic work of Aleknovich, which was then extended by Applebaum et al., to achieve public key encryption, needs delta to be greater than or equal to 1/2. Sorry, that should be greater than or equal to 1/2. So, so in fact, the version of the assumption that we're making is even more plausible in the sense that we're assuming that LPN holds with actually much more error than was needed to be assumed to imply public key encryption. And again, even the public key encryption version has not been attacked successfully in any non-trivial way, as I already pointed out. And so kind of intriguingly, although I'm not betting my life on it in any sense, I wouldn't even bet dollars on it. But as of right now, again, we do not know how to build public key encryption from LPN with delta greater than 0 or any sort of public key, cryptomania type of object. So in fact, this might be a mini crypt assumption, right? It could very well be that LPN with delta greater than 0 is really the kind of a mini crypt. As far as we know right now, it is a mini crypt assumption. And that again distinguishes it from LWE, or in our context also SXDH. So we're making two other assumptions which are definitely cryptomania assumptions, LWE and SXDH. But as far as we can tell, this sort of mild variant of LPN that we're making, assumption we're making, because it has sufficiently dense error, is just a mini crypt assumption. All right. So with that, let me tell you how we're going to use this assumption, because how are we actually going to use LPN? And indeed, we are going to use it to build this new pseudorandom object. So let me talk to you about that. So at the heart of our work, the heart of this new work, is a key pseudorandom object that we call a structured seed PRG. And what makes it different from normal PRGs are a few things, but sort of structurally what makes it different is that the seed has two parts. It has a public seed and a secret seed. And of course, as the name suggests, the public seed is included in the output of the SPRG, so it's revealed to everyone. And it's only the secret seed that is actually kept hidden from the adversary. And this idea of using both a public seed and a secret seed really originated in this line of work, that sort of third generation line of work that Yael talked about, as mentioned here. Okay, and in particular, this notion of SPRG that we are introducing has sort of three main requirements, which I've written out here as 1, 2, and 3. And I'm only going to be talking about the one of them, and then we're going to hear more about the other ones later. So the first requirement, as alluded to by Yael, and as written here on the slide, is this kind of degree 2 efficiency requirement. And again, very roughly speaking, what that says is that the output is a degree 2 polynomial in the secret seed. It's allowed to be a higher degree polynomial in the public seed, but when you look at that polynomial and you restrict it only to how it's depending on the secret seed, it's only degree 2. Okay, and that's absolutely essential for using bilinear maps, as Yael already told you about. Okay, the second requirement is expansion. which is kind of more normal for PRGs. It just says that the length of the structured seed should be m to the 1 minus epsilon. This is yet another constant epsilon.
Amit, by structured seed, you mean the sum of both the secret and the public, yes?
Yes, yes, both the public seed and the secret seed. The length of that should be m to the 1 minus epsilon if the SPRG outputs m bits. So again, it's doing some polynomial expansion on the length of the structured seed. Okay, and there's also a CRS. There's also like a public parameters, which is also allowed, which can be long, but and reusable. However, the actual public seed and secret seed that is sampled each time you use this SPRG, those two together have to have length m to the 1 minus delta. Okay, and then finally, what we need is pseudo-randomness, which is that when you look at the public seed and the output of the SPRG, that is pseudo-random. Okay, and I'm going to explain to you why that's true. And it's an extremely simple argument, and it is the only place where the actual LPN over ZP assumption is used. Okay, and then looking ahead, Rachel will tell us why this object is sufficient to build IO. She'll elaborate on some of the things that Yael just very briefly sketched towards the end of her talk. And then finally, in part 3, Ayush will tell us how we can actually achieve both properties 1 and 2, which are, again, really at the heart of our construction, achieving this degree 2 efficiency and expansion. Okay, but I get to the easy part. I'm going to show you pseudo-randomness. Okay, so let me tell you now what the output of our SPRG will be. Okay, and the output of the SPRG will have 2 parts. Again, this is going to correspond to the public seed and the actual output. And the part that corresponds to the public seed actually looks very much like what we just saw in terms of an LPN sample. So as you can see on the slide right now, the first part of the output will be AI, comma AI.s plus EI, which is just like LPN, but then also plus XI, okay, where each XI is uniformly sampled bits. So there's 0, 1, sampled at random, okay? And then the second part of the output is this kind of annoyingly correlated output. It is the output of a PRG on x1 up to xn, okay? And so, you know, we need to show that these are jointly pseudorandom, kind of despite this annoying correlation, the fact that xi is used in. Can you hear me? I'm getting a notification that my internet connection is unstable. I'm just quickly checking to see if people are with me.
We can hear you.
You can hear me?
Yeah.
Okay.
Yes, we can.
All right. Okay, excellent. All right, very good. So we want to show these are jointly pseudorandom despite this correlation. And there is an insight here, actually, that makes this very easy, which is that in earlier works, in those works that I cited before, there wasn't this LPN error. There was the entire error in the first component was just xi. So the first component used to look like AI, AI.s plus xi, and then the second component was PRG of x. But now we've added this EI. That's sort of this very simple insight that we had of just adding one more error here. Okay, and therefore we kind of separated the error into these 2 components. Okay? And now we're claiming that having done so, proving pseudorandomness is now in fact straightforward. And this is where all of the earlier works were kind of stuck. Earlier, we had to conjecture pseudorandomness of this, and that was basically the assumption that was underlying the earlier works, was that this is actually pseudorandom when you don't have this, this EI part. And now by adding this EI part, we're going to be able to prove it to you in a very simple way. And actually, I'm very tempted, just because I like the idea of having this be interactive. It's very easy to see. Does anyone see why this is true? How would you prove this? How would you prove that this is in fact pseudorandom, despite this sort of annoying fact that we're using xi in both outputs?
Amit, before we go to the quiz part, what's the seed here exactly? A is a public parameter, right?
Yes. A is just a publicly random public parameter, which is just a random L-dimensional vector over ZP.
What's the seed? What's the seed?
So what is what, sorry?
What is the seed here in the pseudorandom number generator?
Okay, so the P, good question. You're talking about the SPRG, right? I want to postpone answering that question, but roughly speaking, the seed corresponds to S, the EIs, and the XIs. So think of the vector S, think of this EI, and think of XI as being the seed.
Okay.
AIs are all part of CRS, and so the output are these two parts.
But just to make sure,
Does
so
that work?
what's the gain and what's the stretch here? Oh, you said it and I didn't.
Good. No, the stretch will be because of the PRG. So the PRG is just a classic good old PRG, your favorite PRG. In fact, we'll use a PRG in NC0, so think about Goldreich.
Mhm.
But for this slide, think of your favorite PRG. It can be any PRG off the shelf. So the PRG is expanding. It expands by a polynomial factor. It has n to the 1, like n to the 1 plus epsilon outputs. And that's where our expansion will be coming from, looking ahead. But right now, I'm agnostic to that. Let PRG be your favorite off-the-shelf PRG, whichever one you like best. And all we need to claim is that for any PRG, these two outputs together are jointly pseudorandom. That's the quiz part of the workshop.
So in this case, you're just, AI.S plus EI, you're assuming that this is indistinguishable from just a uniform independent thing modulo P, right?
Exactly. Yes. So Boaz got it in instantly, right? So it's extremely straightforward. We start on the slide, you see here the output, the two outputs together, and just observe that AI comma AI.S plus EI, this is exactly the LPN sample. So by the LPN assumption, this is indistinguishable from AI comma UI, right? And then the reduction here can just choose XI itself, and there's just a trivial reduction. So the LPN assumption immediately implies that this is indistinguishable from AI comma UI plus XI, right? And then of course, if UI is already uniform, if I add a random bit to it, that's still just uniform, right? This is these are just identical distributions. You can just think of this as AI comma UI, and then PRG of x1 up to xn. But now I've removed the dependency, right? This annoying dependency, this annoying combination is now being removed. And now I can just apply the pseudorandomness of the PRG, again, no matter what PRG it is, and replace the output of the PRG with random. So in this extremely simple way, we use the LPN assumption to break up this extremely annoying dependency that was really the thorn in our side for the past 2 years, for more than 2 years. In all our previous works, we needed to assume that a certain object was pseudorandom, and in this extremely simple way, by using LPN as an assumption, we were able to break it up. I want to stress that I haven't told you about the hardest part. That you're going to have to wait. We're going to build up the suspense. For that, you have to wait until Ayush's talk. So I haven't told you about the efficiency aspect of this PRG. That is really an essential part, and the sparseness of the error EI will come up there again in a really critical way. But when it comes to arguing pseudo-randomness, it is completely straightforward. Okay, any questions about that? I hope everyone agrees this is very straightforward. All right, so so that, and again, that's I promise you, this is the only place where we use LPN in terms of the actual assumption. This is the only place in the entire paper. Okay, so what else do we assume? As I already mentioned, LWE is just exactly the same as LPN, except you have Gaussian, small Gaussian error EI instead of sparse error. That too, we assume, is hard with sub-exponential modulus to noise ratio. And due to these beautiful lines of work, Gödel Prize-winning work of Regev and Peikert and Bugursky et al., we know that this version of the LWE assumption is true if the shortest vector problem over general lattices is worst case hard to approximate to any sub-exponential factor, again, to any arbitrarily small sub-exponential factor. So that's the other assumption. That's the LWE assumption that we make. I also want to point out that just like with LPN, there's also a source to decision reduction for LWE. For example, due to Michian, Chu, and Moll, this is well known. And as all of you know, LWE has turned out to be incredibly versatile as an assumption in cryptography, most famously for fully morphic encryption, the breakthrough work of Bugursky and Vikram. So we all know LWE well, we use it. And before I move on, I do want to just mention that this little pseudo-randomness analysis that I just gave, note that I didn't actually use anything special about the LPN distribution of error versus the LWE distribution of error. This analysis of pseudo-randomness would have worked just as well if these EIs had been small instead of sparse. So then why are we doing it? Why are we using sparsity? It's because the sparsity turns out to be crucial for computing the SPRG. So this degree 2 computation that we need in the secret part of the secret seed, that is another place where sparsity will come back in an absolutely critical way to allow us to do that. Yeah.
While I said that we will not be sticklers with time, let's try to not go too much over time. So maybe
no worries. I'm almost done. So so that's just a little preview. And then we also assume the existence of PRGs because that are computable in NC0 with polynomial stretch. This has been extensively studied since the work of Goldreich. And I think I mentioned, maybe not everyone knows about, there's this beautiful work of Benny and others, which shows that, in fact, this type of pseudo-randomness assumption in NC0 follows from one-wayness conjecture. So if you're willing to assume sub-exponential hardness of inverting the Goldreich one-way function, then that also implies that there are PRGs in NC0 with polynomial stretch. And then finally, we also assume the SXDH assumption over bilinear maps, and this is extensively studied and used. I'm not going to specify it just because the details of the actual assumption are not important, and Rachel will tell you about sort of the actual aspect of the bilinear map that we're using. So, and as Yael already mentioned, as I've already mentioned, in order to get to IO, we do need to make all these assumptions against sub-exponential time adversaries. If we only want to build functional encryption, then we only need these assumptions against polynomial time adversaries. So we do also have a consequence in our paper of building functional encryption, which only requires polynomial assumptions. But if you want IO, then we have to make sub-exponential time assumptions. And that's it. So what you're going to see up ahead in Rachel's talk is how to use SPRG together with a bunch of other things that have appeared in earlier works to get to IO, elaborating on what Yael said at the end of her talk. And then in part 3, Ayush will tell you how to actually build how to achieve the efficiency property of the SPRG, the sort of properties 1 and 2, the degree 2 property and the expansion property, assuming PRGs in NC0 and the sparseness of the error from LPN. And with that, I'll conclude.
Thank you. Thank you, Amit. This is very exciting, and yes, people can ask questions. If you're breaking off, you can go also to the Gather space if you would like to. I can put the link here in the chat, if it lets me. Yes. And but people can ask questions, and yes, the next talk will be at 11 minutes from now at 1:30 Eastern, 10:30 Pacific, or probably, unless you're in India, it's 30, when the minute clock shows 30 wherever you are.
All right. Any questions?
So if there are no more questions, let's take the 10-minute break so people can stretch and meet up again in 10 minutes.